Hello, my name is Muhammad Al-Qasemi, and I'm going to give a presentation about secure and efficient software-based attestation for industrial control devices with ARM processors. This presentation is based on a research paper provided in a link below by the following contributors: Binbing Chen, Xing-Chou Dang, Guangdong Bei, Samit Johar, and Quenyang Cheng. In this presentation, I will give a quick introduction of the attestation process. I'll also discuss the thread model on a low-end ARM processors. I'll also talk about what SWORD is and how it works. I'll also discuss full memory walk versus partial walk. I'll also talk about memory stride design and its implementation. Also, I will talk about evaluation of SWORD in a real-world setting. And finally, I will give a conclusion. ICS control critical infrastructure like power grid and metro system. They need to be secure and resilient against cyber attacks, and if they have been compromised, they are considered a national security threat, as many people's daily life will be affected. There are two ways of securing ICS devices. First type is through equipping ICS devices with secure hardware. The second type is through having secure software-based solution running on those ICS devices. Secure hardware, although preferred, is an expensive solution to implement on a large scale, whereas secure software can be scaled and also be cost-effective. In this presentation, we'll be discussing securing ICS devices through providing software-based solution that can be trusted by going through an attestation scheme. Low-end ARM processors are usually in the field and are intended to be in service for 10 years or even more. Not all ICS devices in the field are remotely accessible through Internet. ICS devices that are unreachable remotely are called air-gap devices. Techniques that penetrate the air gap in ICS constitute an attack vector. An example of such attack vector are as follows: a PC with a malware connected to an ICS device while diagnosing, a vendor or an operator plugging in a USB drive into an in-network PC, swapping an ICS hardware with a hardware that contains a malware. What is software-based attestation? Verifying the software integrity, or rather attestation, is conducted based on some form of establishing root of trust on the devices under attestation. This attestation process can be accomplished by calculating a checksum value on the data stored in the RAM of ICS devices and making sure that this hasn't changed while those devices are running. This process introduces us to the SWORD scheme. SWORD is basically an abbreviation for Software Only Root of Trust, which is a scheme that uses the following elegant idea. If the running copy of a carefully designed checksum software is unmodified, it would be able to compute a checksum over its own memory footprint faster than any modified version. Intuitively, the checksum seeded with some random nouns is a fingerprint of an authentic executable image, and a modified software needs to do some extra work in order to hide its different memory footprint and return the correct checksum. ICS devices have a high availability requirement. An example of that is a BMU unit, which is a phasor measurement unit that requires message delivery within 20 milliseconds, usually used in 50 Hz power grid. SWORD scheme also has to take into consideration of proxy attacks, where devices under attestation ask a computationally more powerful remote device to compute the checksum. Short attestation time helps raise the bar for launching proxy attacks. For example, if a SWORD process completes within 20 milliseconds, a proxy attack behind a slow link would fail. The takeaway point here is that SWORD scheme must be faster than 20 milliseconds to adhere to this requirement. SWORDs work by having a trusted BC or ICS, we call here verifier, generating a random nouns and sending a checksum request with the nouns to an untrusted BC or another ICS device, we call here proofer. Once that request gets to the proofer, it performs a checksum calculation on its entire memory space. Once it's done, it sends that request back to the verifier, and the verifier can be assured of the integrity of the software image or firmware on the ICS device if and only if the received checksum from the proofer is as expected, and also if this received checksum was received within the predefined time constraint, usually 20 milliseconds for low-end ARM-based devices. The basic idea of a memory stride design, which is the heart of SWORD scheme, is to conduct a random walk on two subsets of addresses in the memory in an interleaving manner. One subset is the memory area that hosts the actual attestation code of size capital L, and another subset of size S divided by L is the group of memory addresses called stride addresses that span across the whole memory of size S, with two neighboring stride addresses placed L distance apart, as shown below. Memory stride technique help in reducing the time needed to establish the root of trust on ICS devices, and it defends against all known attacks on software-based attestation and their advanced variant on ARM platform without having to access every memory word. The running time to do the walk on the entire RAM address space is in order of L plus S divided by L overhead. Full memory walk versus partial walk. For full memory walk, the overhead of the full memory walk scheme, which generates the checksum, depends on the number of iterations n and the overhead of each iteration. For the overhead per iteration, it needs to be around 30 CPU cycles even for low-end ARM devices. The dilemma of this scheme is that the number of iterations n increases linearly with increased RAM size on ICS devices, which results in more time needed to perform the attestation and generate the checksum on the entire memory space, rendering it an impractical solution in ICS attestation procedure. For partial memory walk, unlike full memory walk, there are unchecked memory regions in partial memory walk, which can be used by an attacker to launch memory copy attacks. The memory copy attacks potential leverage on ARM devices are free piggyback shift. In ARM-based devices, various logical and arithmetic operations allow for a shift operations for up to 32 bits to be piggybacked for its second operand on the same CPU cycle. Free offset shift with LDR. The LDR pseudo instruction can take an immediate value as a constant in loading the content of the memory address into a register. Free here indicates that the shift is happening without incurring additional CPU cycles. Memory stride design. The security of our memory stride technique depends on the following simple observation. An attacker can potentially shift either the stored code region or the stride addresses around the RAM without increasing the checksum computation time. The only constraint for the attacker is that it has to shift the whole code region as a continuous whole and move all the stride addresses with the same offset. Otherwise, some conditional check will be needed by the attacker, which incurs additional CPU cycles. This design guarantees memory content integrity, regardless of how the attacker shifts the address space. When performing the memory walk over the core region, it needs to return the expected memory content for the core region. And similarly, when performing the walk on the stride region, it should return the memory content of the stride addresses. Here's the pseudocode for the memory stride algorithm. The key points are there are 16 directly accessible registers used, which are register 0 to 15. Register 0 is used to start the random address generator. Register 1 to 12 is used to store the nouns from the verifier. Register 13 is the stack pointer. Register 14 is the status register. And the last one, register 15, is a program counter. Notice here that the memory addresses and the register states are factored in the checksum calculation, which makes it harder on the attacker to shift the memory strides and generate the same checksum as the verifier. Evaluation of a SWORD scheme in real-world settings. The authors of this research paper have conducted a real-world test on how the SWORD algorithm performs over two different variants of RTUs, which are remote terminal units that are used in the power grid. Those two hardware variants have two popular ARM-based processors, which are ARM7 and Cortex-M3. In this experiment, the SWORD code, including the code needed to establish the communication of a TCP/IP TCP network stack to those RTU devices, have been accounted for and deemed to fit in the first 2 KB of RAM space. After running the experiment and comparing the results between the full RAM walk and the memory stride scheme shown in the table below, we've noticed the following. For both ARM processors, it took less than 20 milliseconds to complete the attestation procedure and establish root of trust within 10 nines and 5 nines accuracy. 10 nines and 5 nines here indicate the probability that an attacker will lose to satisfy root of trust requirement. Root of trust requirement here means passing the checksum calculation within the specified time constraint. We've also noticed, as we saw before, that with increased RAM size, the full RAM walk time increased linearly, whereas memory stride scheme have saved us 20 times the time needed to satisfy root of trust requirement. Another test has also been conducted to measure the round-trip time delay incurred from adding up to 10 hops or network switches between the verifier and the broofer. If the communication between the verifier and the joiner broofer is delayed beyond an acceptable response time threshold, the broofer cannot be attested successfully, and this leads to a false positive result. From the test result shown below, it appears that with added hops, a longer round-trip time is incurred, which increases the false positive rate, in which SWORD scheme detects an untrusted devices in place of a genuine broofers. SWORD scheme need to take the network topology into consideration, and the allowed time for the checksum response should include both the computation time for the checksum and the minimum communication time between the verifier and the broofer. In conclusion, the memory stride technique provided a secure partial memory walk solution that can significantly reduce the attestation time on ARM-based devices. This solution can attest real-world ARM-based ICS devices significantly faster and can meet stringent requirements by some time-critical power grid applications. Thank you.